Hello everyone, I'm Hesheng Wang from Shanghai Jiaotong University. Today my topic is vision-based automatic control of deformable objects. This is a part of work on video observing. In this talk, I will mainly focus introducing this part, vision-based automatic control of deformable objects. And if you are interested in our research, you can visit the homepage of our lab. Deformable object manipulation have a wide range of application in many fields, such as food industry, medical and fabric industry, while it is under researched field for challenges that come from the deformation upon force interaction. The higher dimensional, linear, and anisotropy of deformation increase the difficulty of manipulating and controlling. Moreover, when the external effect exceeds a certain threshold, the object will break or separate. Therefore, the automatic operation of the flexible body involved in two important problems. One is that the improper pulling and collision that it can easily damage the flexible body during the deformation operation. And the other one is for the process of separating the tissue, such as cutting. The temporary topology structure will introduce new problems. To contribute to this problem, we propose vision-based algorithm to reduce the dependency on complex deformable objects model and complete the object deformation operation and cutting task. First, we study vision-based tracking control of deformable objects. The objective is to control the image projection of the surface feature point, move along the desired image trajectory so as to realize the control of deformation trajectory in the unknown environment. The basic idea is using the function approximation technology, the so-called FAT, to parameterize the deformation Jacobi matrix and design an adaptive dynamic-based controller to online estimate the unknown parameters, while avoid the sophisticated mathematical problem. The main idea of FAT is that any arbitrary nonlinear function can be approximated by a series of different functions in a certain area. Here is an example of using Fourier series, also Taylor series, and Lagrange series work. We use the weighted basis function to approximate each element of the DGM, and the DGM can be rewritten in the following form. Notice that the coefficient matrix D is time invariant, so we can treat it as the unknown parameters to be adaptively estimated. As for the controller design, the block diagram of the proposed controller system is shown in this figure. The adaptive algorithm for the online estimation of D is as follows. The first compensate for the error in the closed-loop system caused by the estimate parameters. The second term is to improve the maneuverability of the system, which is realized by introducing a virtual force that drives the estimate parameters away from the value resulting Wt equal to 0. The last term is used to avoid parameter drift reference the classic Thornton-Lee's modification method. The controller with visual feedback and the joint feedback is designed as follows, guaranteeing the convergence of both position and velocity error. It can be proved by the Lyapunov theory. The detailed proof you can reference to our paper. Experiment result with different type of deformable objects, including 1D cable, 2D clothes, and 3D spoon, which validate the feasibility of the proposed algorithm. Next, we will introduce the vision-based automatic cutting control algorithm. Compared with the general operations, cutting is a more complicated task. Time-varying topology means more complicated deformation characteristic. During the cutting process, the cutting trajectory will change or even invisible because of the deformation, which is not considered in previous research. To contribute this problem, first we predict the object's deformation and plan cutting paths online, and we visually control the cutting tool's pulse to achieve higher operation accuracy. Moreover, we estimate the material parameters, so we do not need prior knowledge of the object's materials. As seen in this figure, the object of this task is to control the knife cutting soft tissue along the desired path, which is a green dashed line with specific cutting depth. The proposed algorithm can be divided into two main parts. In the first part, the current position of the trajectory point during the robot's motion will be predicted using improved deformation model. Actually, it is improved deformation model, which is obtained by integrating the Kelvin constitutive equation into the traditional spin mass model, considering the with elasticity of the soft tissue. It should be mentioned that the position and the geometry of the object are known, but the material parameters are unknown, which will be online estimated by the visual measurement of the feature point in the method of the UPF. According to the position of the trajectory point of deformation, then we propose a method to generate the desired pulse of the knife in real time by online planning the cutting path and automating the position of the cutter. In order to obtain a continuous cutting trajectory, we use cardinal spring interpolation to generate the trajectory of the cutting point. The desired position trajectory of the cutting point is as follows. As shown in this figure, we define the desired position of the knife as perpendicular to the local deformation surface and tangent to the desired trajectory, which can minimize the deformation during the cutting process. According to the current position and orientation of the knife, the current homogeneous transformation matrix of the object frame respect to the knife frame K is T, while S is the unit tangent vector of the desired cutting trajectory. A is the normal vector of the local deformed surface, which can be obtained by the pseudo-norm vector. Since the knife can be regarded as a plane with a fixed size, the real-time desired position of the knife can be projected onto the image plane to form a target surface. Now the cutting control task is converted to a region-based visual tracking control problem. That is controlling the knife's projection to track the desired surface in the image plane. To couple with this problem, we choose two parallel linear segments, including the direction and the length, extracted from the edge of the knife's projection as the image features, which have the one-to-one mapping with the pose of the knife. Although there are many ways to uniquely determine the plane, such as we choose three non-collinear points, two parallel lines, and so on. However, points may not be detected during the short-term partial occlusion, may result in the control algorithm failure. For lines, it can full use of the natural feature of the knife and easy to detect even if the line detection is incomplete due to the short-term occlusion. The normal vector of the line can also be determined according to the incomplete line segments detected. According to the target surface on the image plane, the robot is manipulated to control the knife's projection to track it in the real time. Video feedback and joint feedback are both into the proposed controller, and it can be proved by the upon analysis. The position and velocity error of the select visual feature will asymptotically converge to zero. This is a video of the experiment. We conduct the experiment with different type of deformation object, including the sponge, artificial tissue, chicken breast, and pork liver. On the surface of the object, there are a series of feature points or read markers that we use to estimate the unknown material's properties. The initial pre-designed cutting trajectory, which is purple line, will also marked. It should be noted that this trajectory is only used to evaluate the cutting performance. It's not used to provide real-time visual feedback. Besides, a series of whitened markers were fixed on the surface of the deformable object, and the position of the marker is used to measure the cutting depth so that the cutting performance can be verified precisely. In the image plane, the blue region represents the desired trajectory, which was calculated by trajectory point of the deformation, And the desired cutting depth, the green one, was the projection of the knife extract from the image and represent the current image features. The cutting task transformed to the image plan is to control the knife, the green region, track the target surface formed by the motion of the blue region. We say that the controller have the good tracking performance, and the experiment result prove the proposed algorithm can realize the automatic control cutting. For the automatic cutting task, we have also made the following attempts, introducing the force sensor to constrain the interaction force. We expect to minimize the cutting force while cutting along the trajectory. By comparing the different cutting trajectory, we find that the resistance of the cutting tools can be reduced by adopting the pricing and sliding approach. Just the online planning of the trajectory are performed based on the updated position of the trajectory point and the um, addition of the force feedback correction. In this way, precise cutting with smaller deformation can be achieved. This is an experiment demonstrate of automating cuts using the method of the pricing and slicing. It can be seen from the figures that the interaction force under the cutting stretch is smaller than the under the pure slicing. That's all for my presentation. Thank you. If you have any further question, please contact me through email. Thank you.